Welcome to the world of basic electronics. In this section, we'll explore the fundamental components that form the backbone of all electronic circuits. Let's dive into the realm of semiconductor devices. Interviewer, explain the working principle of a MOSFET and its advantages over a BJT in power electronics.
A MOSFET is a voltage-controlled device that uses a gate voltage to control the flow of current between the drain and source. It has high input impedance, fast switching speeds, and low power loss, making it more efficient than a BJT for high-frequency switching applications like DC-DC converters and motor drives.
Moving on, let's discuss diodes and rectifiers. Interviewer, what is the difference between a Schottky diode and a standard PN junction diode?
A Schottky diode has a lower forward voltage drop, around 0.2 to 0.3 volts, compared to a PN junction diode, which is about 0.6 to 0.7 volts. This makes it more efficient for high-frequency and low-voltage applications. However, Schottky diodes have higher reverse leakage current and lower breakdown voltages.
Now, we will delve into circuit design, specifically focusing on hardware development. Interviewer, walk us through the design process of a buck converter. What are the key parameters to consider?
The design process involves selecting the input and output voltage, calculating the duty cycle, choosing the inductor and capacitor values for the desired ripple current and voltage, and selecting a MOSFET and diode with appropriate ratings. Key parameters include switching frequency, load current, and efficiency.
How do you select MOSFETs or IGBTs for a high-power inverter?
For MOSFETs, I consider parameters like RDS1, gate charge, and breakdown voltage. For IGBTs, I look at collector-emitter saturation voltage and switching speed. The choice depends on the application's voltage, current, and switching frequency requirements.
What are the best practices for PCB layout in high-frequency switching circuits?
Best practices include minimizing loop areas to reduce EMI, placing decoupling capacitors close to power pins, using ground planes for noise reduction, and routing high current paths with wide traces. Proper thermal management is also critical.
What tools do you use for testing power electronic circuits? How do you design overcurrent and overvoltage protection for a power supply?
Overcurrent protection can be implemented using current sense resistors and comparators to trigger a shutdown. Overvoltage protection can use Zener diodes or crowbar circuits to clamp the voltage and protect the load.
Which microcontrollers or DSPs have you worked with for power electronics applications?
I have worked with microcontrollers like STM32 and DSPs like TIC 2000 series. These are ideal for implementing PWM control, feedback loops, and communication protocols in power electronics systems.
Explain the difference between open-loop and closed-loop control in power electronics.
Open-loop control does not use feedback, making it simpler but less accurate. Closed-loop control uses feedback, such as voltage or current sensors, to adjust the output, ensuring better accuracy and stability, especially in DC-DC converters.
Which programming languages are you familiar with for embedded systems? How do you integrate communication protocols like I2C, SPA, or CAN in a power electronics system?
I use microcontrollers with built-in peripherals for I2C, SPI, or CAN. For example, I've implemented CAN for communication between a motor controller and a BMS in an electric vehicle.
Advanced topics, the topologies and converters. Compare the advantages and disadvantages of buck, boost, and buck-boost converters.
Buck converters step down voltage efficiently. Boost converters step up voltage, and buck-boost converters can do both. However, buck-boost converters have higher complexity and component stress compared to buck or boost converters.
Renewable energy systems. How do you design a solar inverter for a grid-tied system?
A grid-tied solar inverter converts direct current from solar panels to alternating current synchronized with the grid. It involves MPPT, or maximum power point tracking, DC-AC conversion using an H-bridge, and ensuring compliance with grid standards like IEE 1547.
What steps do you take to ensure your design meets EMI/EMC standards?
I use proper PCB layout techniques, shielding and filtering to reduce EMI. I also perform pre-compliance testing using spectrum analyzers and ensure the design meets standards like CISPR 22 and FCC Part 15.
How do you analyze and improve the thermal performance of a power electronics system?
I use thermal simulation tools like ANSYS or FLOTHERM to analyze heat dissipation. Improvements include using heat sinks, thermal vias, and active cooling methods like fans or liquid cooling.
Section problem solving and scenario-based questions. A DC-DC converter you designed is overheating. What steps would you take to diagnose and resolve the issue?
I would first check for excessive current or voltage stress on components, verify thermal design, like heat sinks and airflow, and ensure proper PCB layout. If needed, I would reduce switching frequency or use higher rated components.
You notice excessive ripple in the output of a buck converter. How would you identify the root cause and fix it?
Excessive ripple is often caused by inadequate filtering. I would check the inductor and capacitor values, ensure proper PCB layout, and verify the switching frequency. Increasing the output capacitor or inductor value can reduce ripple.
A motor drive circuit is causing EMI issues. How would you address this problem?
I would use proper shielding, add EMI filters, and ensure good grounding. I would also check for high-frequency noise from switching devices and use snubber circuits if necessary.
A power supply design is not meeting efficiency targets. What changes would you make to improve efficiency?
I would optimize component selection, for example, low RDS on MOSFETs.
And that's how we tackle some of the common challenges in electronics design. Thank you for joining us.
Absolutely, it's been a pleasure discussing these important topics. To minimize power losses in your circuit, you should look for components with low RDS on, such as MOSFETs with low ESR capacitors. Additionally, reducing switching losses by adjusting the frequency and improving thermal management can significantly minimize losses.
In this scenario, we will explore how different design choices impact the efficiency of power electronics. From selecting the right components to optimizing thermal management, every decision plays a crucial role.
It's essential to consider the trade-offs between switching frequency and efficiency. Higher frequencies can reduce the size of passive components, but may increase switching losses.
Balancing these factors can lead to a more efficient and reliable design. Now let's examine a real-world application where these principles are put into practice. Imagine designing a power supply for a high-performance computing system.
In such a scenario, choosing components with low RDS are one, and optimizing thermal management are critical. This ensures that the system can handle high power levels without significant losses or overheating.
By carefully selecting and managing these elements, you can achieve a highly efficient power supply. In our final scenario, we address the importance of ongoing monitoring and maintenance in power electronic systems.
Regularly checking for signs of wear and tear, such as increased thermal resistance or changes in component performance, can help prevent failures.
Proactive maintenance not only extends the lifespan of the system, but also maintains its efficiency over time.
Absolutely. Keeping an eye on these factors ensures that your power electronics continue to perform optimally.